Well, it is a pleasure to be here this evening. I always enjoy coming to Flagstaff. Been to Phoenix, and it's a lot nicer up here. I wouldn't say that in January, maybe, but it is good to be back. I went over to Lowell today and had not been there in 13 years, and nice to see the changes there. Well, the James Webb Space Telescope launched Christmas Day a few years ago. It was nice that he launched on the anniversary of the birth of Isaac Newton, so it's a really exciting thing. Took about 6 months to get the shakedown done. And I'll explain a little bit of what that involved. They had to do some calibration, but they had other things before that. So it took 6 months to get some photos coming. And, it's interesting what's been coming out. The title, of course, is What's Revealed About the Universe. And it's really exciting what we've been seeing. And about a year and a half ago, at Genesis and Genesis, somebody emailed in and they heard something about some result. And it was all about evolution and billions of years and so forth. And they were very concerned. They wanted to know, and they said in there, they wanted to know about this discovery by the Jack Webb Space Telescope. The Jack Webb Space Telescope. And I was immediately amused by that one. So I wanted to answer that. And I want to distinguish between the observations and the interpretation. And so I wrote back and I said what the James Webb Space Telescope has observed are the facts. Just the facts. And then you have the interpretation to all of that. So anyway, there were two prime objectives for the Space Telescope to do with the James Webb. I'll just call it the JWST. It's a lot simpler to say. And with the HST, there were two prime objectives. When they do a project like this, they generally have one or two or three big things they want to do. Now, they can do other things as well, but the thing was designed to look at two particular issues. And the first one, the one we've heard the most about so far, is to study the structure and evolution of stars and galaxies in the early universe. And I'll talk more about that in a minute, what that means and what that means to us as well. And the other one was to look at the atmospheres of the compositions of exoplanets. Exoplanets are planets that are orbiting other stars than the sun. Does anybody know how many exoplanets are now known? Anybody? Want to guess? 15. Any more guesses? Well, a few years ago, we had we crossed the threshold of 5,000. Well, you're a little short there. The first one was discovered about 30 years ago. It's amazing how has increased. I'm sure we're going to hit 6,000. Maybe we already have. The last time I checked, we weren't there, but I haven't checked in a while. So we're finding lots and lots of these things. And why are they looking for exoplanets? Well, they want to show that solar systems or stellar planetary systems like the solar system are common, and they want to show that Earth-like planets are common, which then they're going to prove, give evidence that life in the universe is common. And you can see the evolutionary underpinnings of all of that. So they just really kind of started on that. I'll come back and talk about that more, but I'll talk about the first one for the most part. Before I do that, I need to address just exactly what the JWST is and what it's not. And many times when they were launching it, it was compared to the Hubble Space Telescope, the HST. They were saying it's the replacement of the HST. Y'all heard that before? It really isn't the replacement because it's a very different telescope. How are they different? Well, the HST you see photographed here, first of all, it's an optical telescope, which means it's working in the visual part of the spectrum. And it goes a little into the ultraviolet, which is wavelengths a little shorter than the visible we can see. And it goes a little bit in the infrared, but not very far, wavelengths longer than what the eye can see. But basically, it matches what we can see, what we traditionally, astronomers for 400 years have been studying with telescopes. It was put above the Earth's atmosphere because we have a blurring effect on the things that we see. And if you get above the Earth's atmosphere, you don't have that. So you get sharper detail and deeper coverage because you don't have the atmosphere scattering light either. There are other reasons for putting space telescopes up because you can reach parts of the spectrum that don't reach the ground. The Spitzer infrared telescope is one of those. You also had some X-ray telescopes, ultraviolet telescopes. None of those wavelengths make it to the ground. And so if you want to study those, you have to get above the atmosphere. The Hubble didn't do that because the Hubble was just simply doing something in the visual range. The size of the Hubble Space Telescope is 2.4 meters. That's about 8 feet or so, something like that. It's a big telescope. It's at the bottom, lower right in that diagram, that photograph you see. The light comes through that over the top. You got this cover that can be moved up and down. The light comes through and the cover's up. Hits that mirror, comes back up to the secondary, and then finally the several instruments that they have aboard this. 2.4 meters 100 years ago would have been one of the largest telescopes in the world. The Mount Wilson telescope is 100 inch, just slightly larger than that. So it would have been a world-class telescope on the ground 100 years ago. It's still a respectable telescope, particularly when you consider it's in orbit. It can have incredible resolution that you can never get on the ground because the atmosphere blurs the images so much. And it has, by the way, do you realize they launched the HST 35 years ago? Yeah, it's a long time. They've had several service missions to it. The space shuttle wouldn't go up in service. Well, they don't have the space shuttle anymore, so there are no more planned missions to go do upgrades on the thing. And it also needed to be boosted from time to time because orbits of lower satellites, they decay, the wind resistance. There's actually a small amount of gas up there. It slows it down and they slowly spiral down. If you don't boost it, then eventually they'll fall into the Earth's atmosphere and burn up. And it would probably burn up all except for that mirror. That mirror is going to survive when it hits somewhere, probably in the oceans. And the plan that people want to do a rescue mission so they can bring the thing back to Earth. We don't have any capability of doing that now, so it's kind of a nice idea. Without a shuttle, it's kind of hard to do. Also, it has a single mirror. It's a single piece of glass at the bottom there, and again, it's in low Earth orbit, which allows you to do servicing. And that's going to be a huge difference. In fact, everything here is going to be very different on the JWST, which I questioned then. It's so different from the HST. Is it really a replacement? Okay. Now here's I guess this is a generated image. It's not a photograph of what the JWST looks like. And the thing is, it's an infrared telescope, entirely infrared. In fact, pretty deep in the infrared. You can probe into the infrared a little bit. But this is far beyond that. It goes pretty far mid and far infrared. So it's got, I think it's got six channels that it looks at. So you can take photographs and images in six or seven channels, and you can get different images and compare them. Now we can't see infrared with our eyes, but you can detect it. Everybody do this. Take your hand and hold it just about a half inch off your face, and what do you feel on your cheek? You feel heat coming off. What you're feeling is infrared radiation coming off of your hand because we're fairly warm. We glow in this. Anybody ever look through night vision goggles set with infrared? When you do, you get this ghostly green or white thing, and you see this outline of a person walking around because we are quite warm, warmer than the surroundings typically. Now, pit vipers, like rattlesnakes, they can't see very well. Their eyes can see light and dark, and that's about it, pretty fuzzy. But the reason why they're called pit vipers is because that triangle-shaped head, they have on either side these openings, pits, that are infrared detectors, and they actually can form images. So if you were in a totally dark room, and there was a pit viper in there, it would basically see what you see with night vision goggles in the infrared mode. Now, don't be afraid, he's not going to come after you because we're big, we can't eat us, and we represent a threat. So they'll probably leave you alone for the most part because it's not an aggressive snake. But that's an example of that. Also, it's used in technology such as with missiles to take down airplanes. They're heat-seeking missiles. You launch one, and it's looking for something really hot, and the really hot is the exhaust of the jet. And so what most of these missiles do is they go right up the exhaust port on the engine, blows up, and jets don't fly very well when they don't have engines anymore. They don't have to blow the plane up. They just got to blow the engines up, and it's over. So infrared's all around us. Hot things have that. In fact, anything with any kind of temperature has some infrared signature. Even the furniture in this room, even though it's cooler than we are, it will give off infrared radiation as well. Now, so you have false color images when you see these. Its size is a 6.5 meter aperture. 6.5 meters. That's 2 or 3 times the size of the HST. The diameter of that mirror is over 20 feet, like 22, 24 feet. It's big. And so it has a little more light gathering power, about 7 or 8 times the light gathering of the HST. So it's going to collect a lot more light there. And it's different, it doesn't have a single mirror. As you can see in the diagram there, you get this honeycomb sort of thing. And these are all hexagon mirrors, and they're coated with gold. Why do we coat those with gold? Because we're NASA, and we've got scads of money to waste. Well, no. As it turns out, gold is highly reflective in infrared. You remember, if you've ever seen pictures of the lunar excursion, in fact, look at it, right? There's a photograph right there in the back, lunar excursion module, I think on the Apollo 17. You see all that gold foil on there? See what I'm talking about? For many years, I didn't know why they put gold foil. I could see the pictures, and they said it was gold foil. I thought, why are they doing that? Because it's NASA. They got billions of dollars to waste, you know? No, much of the sun's radiation is in much of the energy it delivers is in the infrared part of the spectrum. And they needed to keep the parts of the lunar lander cool. And the way to do that is put that very thin foil there. It reflects almost all the solar radiation that hits it because it's a very good reflector. The infrared radiation is mostly blocked by the Earth's atmosphere, largely by moisture, but other things. That's the reason why Phoenix gets so hot in the summertime, 110, 115, 120, is because it's really dry in Arizona. Yeah, it's really dry, and the moisture in the air will absorb that, so block it from coming in. But if you're in a really dry location, you get all this visible light coming in, but you've got all this infrared coming in too. Not much of the spectrum, but enough to make a difference. That's the reason why where I live in Kentucky, it never gets to be 110, because we've got too much moisture in the air. But at night, the reverse happens. The Earth radiates away, and it passes right through that pretty dry air. Now, I know there's a heat island effect going on in Phoenix today. If you go out in the desert, it still cools off at night quite a bit. So it goes both ways. So that just talking about this infrared, what it can and can't do, and again, the gold, why they're using gold on that. All right, the place it's in orbit is not in low Earth orbit. It's what's called an L2 orbit, a Lagrangian 2 position. And I'll come back and talk about that in just a minute. I want to introduce that to you. Now, it's a very different kind of orbit than the HST ever had. And notice the large sunshade. That's that thing on the bottom. It looks white. It's got like 6 or 10 layers. It's a thick thing there. That thing is as big as a tennis court. It's huge. And I'll explain why they have to have that sunshade here in just a minute. In fact, well, maybe I'll go ahead and explain it right now. No, I'll wait. I'll come back and talk about it. Okay, let's go talk about the Lagrangian points. I have here a diagram of the Earth's orbit around the sun. The yellow circle in the middle, of course, is the sun. And then you have a blue circle. That is the Earth's orbit. On the right is the location of the Earth at that time. There's a little red circle around it. If you look very carefully, that's the moon orbiting around the Earth. Everybody clear what's going on? We're going to ignore the moon for right now. Just look at the sun and the Earth. And what causes the Earth to go around the sun? Well, it's the gravity of the sun pulling on the Earth, and it goes around like that. Now, this is the Sun-Earth system we're talking about. I want to emphasize that this drawing is not to scale. The Earth is very large compared to the sun. The sun's diameter is more than 100 times that of the Earth, so the Earth would be very tiny on this. And the distance between the two is greatly exaggerated. The distance between the Earth and the sun is something like 12,000 Earth diameter. So you couldn't draw this to scale, would look like anything you could recognize. Now, I already pointed out that the orbit of the Earth around the sun is caused by its gravity, and that's what's called a two-body problem. And Isaac Newton solved this when he was doing his Principia 350 years ago. And when you do have two bodies like the Earth and the sun orbiting each other, it will get you a nice algebraic solution. A person with good high school math can work this out. You'll have an elliptical orbit, and you'll get the other two laws of Kepler with planetary motion. It's again, your high school math background will allow you to do this. It's a nice closed form that you do with all that. But what if you throw a third body into that system? Like the moon, for instance, or Venus or Mars, a third object in there. Well, now it gets very complicated because we were just considering the effect of the sun on the Earth, but now you have to figure the effect of the sun on this third body, and the third body on the sun, the third body on the Earth, and the Earth on the third body. As it turns out, there is no single simple solution. It doesn't have a closed form, we would say. And Newton was well aware of that. So we call this the three-body or the n-body problem. If you have two objects, you can solve it relatively straightforwardly, but as soon as you put a third object in there, it's insolvable according to the way mathematics works for us. So it's called the n-body problem because it's not possible to work in a closed form. However, it doesn't mean it can't be solved. For the next 100 years after the Principia, people were working on this. How do we make this work? Newton didn't get it, but other people did. A guy named Euler did a lot of it. A few other people did. In the 1700s, they were working this out very carefully. And what they came upon was a series of approximations. You would start with the sun and the Earth, and you go to the sun and this other body, and then the interaction between the Earth and the sun and this new body. and then you would kind of tweak your solution, and you'd go a second run at iterative process. You make your calculations, you then make a slight change to the calculations, you repeat this, and this thing will eventually converge towards a stable solution. It would take an infinite number of steps to get it to actually a closed system. You can't do that, but with computers today, you can do 100,000 steps if you wanted to, but you reach a point that it doesn't matter much anymore. And so people were very clever doing this by just the pure mathematics 300 years ago, 200 years ago. Today, we can just take it out to infinite precision if we want. So it's doable, but not in a simple way. It's a series of approximations that are done. Now, there is a way to simplify this, though. What if that third body has very little mass? Like, I think of two situations. One would be an asteroid, a few miles across. And asteroids are pretty small, and the mass of the Earth is like millions of times more massive than the asteroid, and that's pretty much nothing. So when that happens, you can ignore that asteroid's mass and treat it like a test mass. And there are these things called near-Earth asteroids, NEA for short. And what that means is their orbit is very similar to the Earth's orbit, may cross the Earth's orbit, which means occasionally one of these rascals may hit the Earth's atmosphere and punch through and hit the ground. It's going to make something like what you see out near Winslow. You've all been to the big hole over there? You know, the first time I went there over 25 years ago, you go through the visitor center and you come around a corner and you got this big picture window and you see it for the first time. I came around quickly and I gasped. It took my breath away because it was bigger than I imagined it to be. On that trip, I went to the Grand Canyon for the first time, and I didn't gasp because I had an idea it was kind of big. But when I got there, I said, yeah, this is big. I'm impressed. But with this, I was really surprised it's much bigger. Anybody else have that impression that the meteor crater it was bigger than you thought? No, it really is stunning. Well, I got news for you. That thing was maybe 50, 100 yards across, if that much. What if something the size of a mile or so came in? That would be a pittance. That crater would be a pittance of what it would do. It could be civilization ending. So you can understand why people want to know about this. So we've got actually some programs out there looking for near-Earth asteroids. And some interesting things are going on. If it's orbiting close to the Earth around the sun, occasionally the Earth's orbit, the Earth's mass will pull on it and actually change its orbit quite a bit. And when that happens, sometimes it can capture one. Did y'all hear the last 10 years? The Earth had a second satellite or moon. Everybody know about that one? And I got past it. And what happened is they discovered this little faint object out there, a few hundred feet across, I think, and it had been captured by the Earth. And it kind of had this weird orbit. Here's the Earth, and it's going like this around the thing. It made these loops and stuff. It did this for a few years, and finally it escaped, and it's orbiting around the sun again. But in the future, it might happen again. Well, a few years later, they found another one. So occasionally, the Earth picks up one of these near-Earth asteroids. It doesn't collide, but it yanks it around, and that's what the solution to the three-body problem is. If the mass is very low, it's actually a lot easier to work out. Not simple, but easier would be if it had appreciable mass. It also works with satellites, because satellites satellites orbit the Earth. These are things that are outside the Earth's orbit, so they're space probes. And they have very little mass. And so if you do that, now when you do this for most bodies, you get chaotic motion. That motion I mentioned about this thing looping around and finally escaping. I've seen diagrams what the orbit was, and it's crazy, but not like the moon's orbit. But a guy named Lagrange a couple hundred years ago came up and he found that there were 5 points that were stable. And that means if a small object with little mass, like a spacecraft or an asteroid, happens to find its way to those points, it will tend to stay there. So like little holes. In fact, we do gravitational theory, we talk about gravitational potential energy, and we can plot it out in 2 dimensions if we want, like a sheet of something. And if there's a hole here, that means it's low gravitational potential. When an object falls in there, loses some energy, it's going to stay there for quite a while. And these are like holes in that gravitational potential field out there. And we actually see some of these taking place around us. Now, I'll describe the 5 points to you. The first point is between the Earth and the Sun. It's a lot closer to the Earth because the Sun has a lot more mass than the Earth has. That's the L1 point. And so if an object finds itself there, it will continue to orbit in that position. By the way, I like to compare these Lagrangian points. sort of like those holes behind the cushions on your couch. If you do that, there's certain places where things collect. That's what they fall in and they can't get out. That's what these things are like. They fall in. I see some grins. Everybody's getting it now, aren't they? So the L1 point is closer to the on the near side of the sun, Earth towards the sun, a lot closer to the Earth than the sun, because again its mass is so different. Now the L2 is on the other side of the Earth, and it's about 1 million miles away from the Earth. That's where we put the JWST. If it's 1 million miles away, is there going to be a service mission? No. So when they put it up there, it had to be right. Everything had to work perfectly, and if it didn't, goodbye $1 billion or two. They were just throwing everything on one number on the roulette wheel table and wanting it to come up. Now they kind of stacked the deck because they knew what they were doing. It wasn't random. They knew exactly what they were doing. Let me tell you about the other Lagrangian points before I go any further. The L3 point, as you can see, is on the other side of the sun. So if something falls over there, it will tend to stay there. The L4 and the L5 are interesting. They are in the same orbit with the Earth, but one's 60 degrees ahead and 60 degrees behind. So that angle from the sun to L4 and L5 is 120 degrees. 60 between the Sun-Earth line and 60 the other direction. Now, we've actually seen this many times. In the late 1800s, they began to discover asteroids around following in Jupiter's orbit, some at L4 and some at L5. And they're called the Trojan asteroids because when they were naming asteroids, then they were starting to go through the account of Homer of the Trojan War, and they were naming them after characters, and that's why they call them the Trojan asteroids. And they're kind of trapped there. They're going to be there for a very long time. And in recent years, we've now found about 1 million asteroids. They found a few in the L4 and L5 points of the Earth and some other planets. We just couldn't find them before because it was so very, very faint. We found them now. So L4 and L5 are also stable but different. They chose to put it in the L2 position. Now, why did they want to do that? Okay, well, this comes down to what the sunshade is all about. Warm things emit infrared radiation. Our bodies do. The chairs in this room do. In fact, anything that has temperature above absolute zero will actually radiate in infrared. I was on an observing run at Kitt Peak National Observatory 40 years ago, mid-80s, and I was working on some stuff with my dissertation that I was working on, and I was using infrared telescope. It was a 50-inch telescope. Well, that's huge. It's over 4 feet the diameter. It's the biggest telescope I've ever used. And it had an infrared system on it. It was fun. It was called the closed cycle cooling photometer, CCCP. So everybody in the hill mountain referred to it as the people's photometer. So it was good. And what it had was a cooling system, liquid helium, and it was a closed system, had a refrigerator on it basically, and it would let the helium expand and chill, and it would come back and pump it back up again. And the reason why I had to do that is because I was looking at these stars. Even then, it was a problem. What they were doing is they were cooling the detector. The detector's down in there, and it was like 10 or 20 Kelvin. It was really like 420 below zero Fahrenheit. Really, really cold, because I didn't want the detector to produce heat and detect its own heat as being part of their signal. Well, I would point it at one of my program stars, and I'd get like 500,000 counts. Well, I knew that I was measuring not only the star, but a little sky around it. So I pushed the telescope off to the side where there's no star, and this is pretty standard in photometry, which I've been doing for 45 years. And I would measure that bit of sky, and I subtract the difference. So when I do visual photometry, I get very few counts. I might get 50,000 counts on a star, maybe 100,000 counts on a star. And when I do the sky, I get like, I don't know, 600. But I need to subtract it off on all of these to make it work. Well, when I did this with the infrared telescope, I got 500,000 counts. So I subtracted the star reading with 500,000 or so counts, and the sky reading with 500,000 or so counts. I got about 5,000 counts. Why was most of my signal background or noise? Well, the detector itself wasn't at fault, but the telescope was. The mirror itself had room to whatever the temperature was outside, and it was blasting all this stuff. Everything in the telescope was doing this. So it'd be like going out tonight using a telescope made out of light bulbs. And you're trying to look through the eyepiece, and you're trying to see the light from a star, but you've got light coming up from the telescope itself. The tube, everything is glowing. That's what you're up against in infrared. And that's the problem. On the ground, you can't cool the telescope. Now, there was the first infrared telescope launched into orbit was IRAS back in the early 80s. And that one had a doer on it. It had liquid helium in it, and you let it expand, and it would cool the mirror itself, and the detector was really, really good. It ran for about 9 months, I think, and then the doer ran dry, and the telescope started to warm up. Couldn't do it anymore. There's a telescope, orbiting telescope called WISE, and stood for something. And when they got done, when the doer ran out, then it warmed up. They could still work with bright objects, so they rechristened this a new system. They got funding for it, what they called NEO-WISE. It was working with that background noise. The Lyman Spitzer infrared telescope was the biggest thing we ever launched in space for infrared observing. It too had a doer. It ran for a while. And if you wanted to, in Earth orbit, low Earth orbit, you could visit with the shuttle and you could replace the doer, put more in there. So you could service it if you wanted to. But you can't do that with the JWST because it's an L2 point, a million miles away. And you wouldn't want to spend like $1 billion wasting all that gold and stuff to put it there for 6 to 9 months, and then it goes blind because of all of this. So they had to think about how they could do this better. And skipped over a couple steps there. The telescope is not cooled in infrared. The earlier infrared space telescopes were cooled, but they had a problem that limited your lifetime. So there's no coolant here for the JWST. So here's what they did. If they would have put it in low Earth orbit, nearly half the sky would have been the Earth, because in low Earth orbit, half the sky almost is there. And all this infrared radiation is coming off the Earth. It would have bathed the telescope itself too, source of heat. So if you put it at the L2 point, at that distance, the Earth would be about 3/4 of a minute of a degree in the sky. Pretty small. So you point the telescope away from that, and you put on the bottom of it this big tennis court sized set of a bunch of sheets of material as insulating material. And by the way, it's more than pointing away from the Earth, it's pointing away from the sun, because remember, you got the sun here, the Earth here, the L2 point here. It's going to move around with the sun like this. So if you put the shade facing the Earth, it's going to face the sun as well. So the JWST is never illuminated by the sun. Has anyone ever told you to take something and put it where the sun never shines? Now you know where that place is. All right. So if you let it sit there for 6 months, what's going to happen to the temperature? If it's not getting any infrared radiation from anywhere, it's going to get real cold, a few degrees above Kelvin. I think it runs like 10 Kelvin or so. It's extremely cold. And so its infrared signature is minimal, almost no infrared signature at all. That's why they put that big tennis court sized shade there. That's why they put it in the L2 point. They were really, really figuring out what to do with this. It's an amazing thing. And again, the problem is if you have to service it for some reason, it's impossible. And the thing is pretty big. The mirrors we put together is more than 25 feet across. And we don't have any rockets with a payload that big. So how do you launch it? Well, notice you got segmented mirrors. So what you do is you hedge them and you fold them up like this. Fold, 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 fold. Those support beams, fold, 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 fold. The big sunshade, fold, 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 fold. And so when they finally got it up to the L2 point, which took a little while, they finally gave the command for the first piece to unfold. And this is just like this. It's like it takes maybe half an hour to do that. And once it walks into place, then you send the command for the next thing to unfold. Remember I said there are like 350 or 400 points of failure? I didn't say that, but I just said it. 300 or 400 points of failure because of that many unfolds. Wow. And if any one of them failed, you've just thrown $1 billion and more of the taxpayers' money. Well, the fact that we're getting information from it tells us that it was perfect. Had to be perfect. One time, no failures. From a government agency, that's amazing. And so it was perfectly put out there, and then it took weeks. It took weeks to do that because you want to do it nice and steady and slow. Then once that sunshade was unfurled and is properly oriented, then you got to wait months to cool down. It cools down quickly at first, and slowly and slowly. And once they started getting cool enough to actually do measurements, then they had to do calibrations. They had to look at known standards, measure those, compare the input they're getting from the detectors aboard the spacecraft against known standards, and calibrate how much flux results in what astral brightness you're measuring. And that took a while. So that's the reason why it took 6 months before any pretty pictures came about. Clear enough? Any questions so far? I'll take Q&A at the end, but if you really need an answer along the way, stop me. Okay. Now, why the infrared? Why the infrared? Well, the big project they wanted to do, number one, was to study galaxies at the early universe. This means they're going to start, first of all, with the assumption of the Big Bang universe. Now, we're not going to assume that tonight, but they're assuming that's in here. And that means that the universe started 13.8 billion years ago. It's been expanding all this time and cooling as it does this. And when you look at a great distance, you're looking at a look-back time. If it were clear tonight, we could probably see the Andromeda Galaxy. How many people have seen the Andromeda Galaxy before? Been on a raft trip with me, you probably have seen it. And anybody know how far away it is? It's out over 2 million light years. And so most astronomers, not me, but most astronomers will tell you that you're seeing the galaxy not as it exists today, but as it exists 2 million years ago, a little over 2 million years ago. Well, if it's 13 billion or 12 billion years old, 2 million years is no big deal. It's pretty close. But what if you go and look at a galaxy that's 1 billion light years away? Well, now you're looking at it when it was 1 billion years ago. Now, if it's been around for 12 billion years, well, that's 8% of its lifetime. So that's not terribly different. But you keep pushing it farther and farther out. If you go out to, say, 12 billion light years, you're now looking at a galaxy that, as it exists not today, but 12 billion years ago. And that's only 800 million years after the Big Bang. And so what you're ostensibly seeing in a galaxy 12 billion light years away is a galaxy that formed in the very early universe. Do you understand what I'm saying here? Everybody clear enough on that? And this is because the redshift that takes place back in 1929, Edwin Hubble discovered that the farther away a galaxy is, the greater its spectrum is shifted to longer wavelengths. We call it redshift because in the visible part of the spectrum, you have the short wavelengths are blue or violet, and the long wavelengths are red. And so if you shift it towards a longer wavelength, that's towards the red end of the spectrum. So we say it's redshifted. And so for nearby galaxies out to maybe 1 billion light years or so, that's pretty nearby, folks. The light is still going to be in the visible part of the spectrum. The part of the spectrum of a galaxy we want to look at is smack in the visible part, as it turns out, the stuff we can see normally. But if you're out 10, 12 billion light years, that light is so shifted, it's no longer in the visible. It's way over here in the infrared. We can't get that from the ground at all. So if you want to study extremely distant galaxies, which within the Big Bang paradigm would be in the very early universe, and you can then sample what galaxies look like and what their structure was and what their composition was by looking at that great distance. They've got a theory. The Big Bang happens, and then after that, stars and galaxies begin to form. And they really want to test their ideas by actually looking at those infinite galaxies. We couldn't do that before because you'd have to work in infrared. We got nothing big enough in space to do that. So you want to look at the far and the deep infrared. So they designed this thing particularly to do that, reaching pretty far. Now, obviously, creationists are not going to agree with some things here. For instance, I said that I wouldn't agree that the light we're seeing from Andromeda has been left there 2 million years ago. With my understanding of the my solution, I should say, to the light travel time problem, I believe we're looking at light that has been traveling for maybe 6,000, a little over 6,000 years. We're seeing the universe in something close to real time. Not exactly real time, but 6,000 years compared to billions. That's real time. It really is. So before I get to the good stuff, let me ask the question: how do the HST and the JWST compare? As it turns out, the HST can get a little into the infrared, and it can take pictures of things. We can take things on the shortest part of the infrared wavelength and get a little overlap here. And so what I have here is a picture of a cluster of galaxies that show gravitational lensing. Gravitational lensing was something predicted by Albert Einstein a long time ago. It wasn't verified until about 40 years ago, long after his death. But here's the idea. You've got a very massive object sitting here, and you are on the Earth, and this thing's pretty far away. And if there's a distant galaxy, the light of the galaxy will pass like this. But as it does, according to relativity theory, the mass here will cause the light to bend a little bit like that. And so you will see the galaxy up here when it's really down here. You may see it down here when it's really up here. So it's acting like a lens to bend light that's going like this to come back around. And this is shown up usually as arcs around it. So here's what a HST photograph looked like. If you look very carefully, there's a cluster of galaxies in the middle. A cluster of galaxies may contain a few thousand galaxies. And each galaxy would have, say, the mass of a couple of 100 billion times out of the Earth, of the Sun. So when you put that together, you've got trillions, quadrillions or more of mass. It's a huge amount of mass. So if you have a distant quasar or galaxy beyond that, you can get gravitational lensing. Now look at the center of that diagram, that photograph. Do you see in places near the center there are these like streaks like this going like this and like this, almost like a bullseye pattern? Do you see it? Yeah, it's pretty famous. You can make it out. That's gravitational lensing. This closer to us, still pretty far away, galaxy cluster is lensing the light of a much more distant source. This is the HST. Now look what the JWST did with the exact same field. It's an improvement, isn't it? What they've done is they recorded in the infrared, and they've then put it in colors, false colors of what the eye might see if you were seeing when it was this distant light was not redshifted so much. Can you see all the streaks now? It's much more obvious there. So obviously it does improve upon the HST, doesn't it? Okay, what about the best infrared telescope we ever had before, the Spitzer Space Telescope? It was a marvelous instrument in its day. Well, I'm going to give a comparison of a spot in the sky done with the Spitzer on the left and the JWST on the right. What do you think? The resolution is stunning. The other one's kind of fuzzy. The one we have now is really sharp. So I'm just showing you a little bit of what the JWST can do. It's a marvelous instrument, what it can do. So what kind of questions must the JWST answer about the early universe? We just talked about why they did maximize it for this. Well, big question is, how early did galaxies form? Okay, how early did they form? And what structure did the early galaxies have? There's an idea that galaxies evolve. Galaxies first form, they are going to be in a primitive or young state, and then they're going to age over billions of years. We consider the Andromeda Galaxy and the Milky Way galaxy that we live in to be mature, if you will, old galaxies. But the galaxies way back there should be very young galaxies. It'd be like comparing a 10-year-old to a 70-year-old. They're going to look a little different. Don't believe me? Look at my pictures when I was a little kid. People thought it was cute back then, believe it or not. All right. What composition did the early galaxies have? And we'll talk about that more in a minute here. And then how have the galaxies evolved since then? Now, you might think that we're just going to take these pretty pictures and we're going to show them to you. But remember, when you're going out 12 billion light years or more, even the JWST is straining. It's really straining to get this light together at this point. So I'm going to just show you a couple of panels here. You got there in the top Macy's galaxy, and you've got 2, 4, 6 things. You've got 6 different channels that's going on, and that's the image showing you Macy's galaxy. And they got it circled there. That other bright dot there, that's not Macy's galaxy. The thing in the little green circle, see the little green circle? That's Macy's galaxy, and it doesn't show up too well in the first frame, but it does in the second and third and fourth and fifth and sixth. It kind of peeks out on that third frame, doesn't it? And that's that little faint object. And the thing I'm smearing across the bottom is a spectrum. You've got what's called the H. Lyman spectrum, and they also identify an oxygen spectral line over there. And you've got the 1 second resolution of there. Then you got below Sears 93316. That name just rolls off the tongue, doesn't it? And they've got it circled too. And notice in the first couple of frames it doesn't really show up well, but on the third frame and definitely by the fourth and fifth and sixth frames, it's showing up very well. And below that is also a spectrum. It's showing lines of hydrogen and oxygen and sulfur. And that's going to be important later on. I'm going to talk about, remember, oxygen and sulfur, and above that, oxygen as well. Now, notice the ages that they have. The Sirius galaxy on the bottom is 1,194 million years old since the Big Bang, as they're saying, according to the Big Bang model. That's going to be 1.194 billion years after the Big Bang. So we're looking at something pretty young. It's only like 1/12 the age of the Milky Way and Andromeda. But look at the Macy's galaxy. Its age is determined to be 390 million years. So that is what, something like 1/50th or 1/60th or so of the age of the Milky Way. So that's going to be a really young galaxy. That one's young, but this one's even younger still. Now, there's this thing called the cosmic dark age. And the idea is the Big Bang happens 13.8 billion years ago. And as the Big Bang unfolds, it's expanding, it's cooling, and the thing is filled with radiation to begin with. It's blindingly bright. And then as it expands, it gets cooler, you get the age of recombination, the universe becomes transparent, and that's where the CMB, the cosmic microwave background, comes from. But still, it's pretty bright. But as it expands, it gets fainter and fainter. And after a few million years, the universe goes very dim. It's dark, truly dark. But then about 500 million years after the Big Bang, the first stars start to form and the first galaxies start to form. So the prediction they have is if you look at stuff within 500, look for things within 500 million years after the Big Bang, you're not going to see anything because they aren't there. It's dark. But the problem is JWST has observed galaxies younger than that. You saw Macy's was almost 400 million. They've since found ones that they think are 200 million and 300 million years after the Big Bang. Whoops. There weren't supposed to be galaxies until 500 million years, and you're seeing them at half or even 40% of that time. So how well did the prediction work? Didn't work too well, did it? Didn't work too well. And also, so we conclude from this that the galaxies were forming too fast. For the model said they're going to form here this time, and they're forming much sooner than that. So they're forming much too quickly according to the models that they have. What about the structure of distant galaxies? Well, the galaxies that first form should have a different structure. If they're spiral galaxies, they won't look quite like a spiral galaxy then. But what they're finding, those galaxies that are only, say, a million light years or a billion light years or half billion light years after the Big Bang, they seem to show full structure. They look like mature galaxies. It would be like you've got a picture of some 6-year-old kid and he looks like me. That's not supposed to be. It would be horrible if that happened, right? And there's virtually no evidence of galaxy evolution. Galaxies seem to pop into existence earlier than they thought, fully formed. Mature, if you will. You all know who Jason Lyle is? He's a creation astronomer. And shortly before the launch of the JWST, he went out there and online published, he says, I predict that we'll see galaxies all the way out. And I thought, that's brilliant. I didn't think of it. I believe that, but I didn't think of saying that's my prediction. I'm proud of him for having the insight that I lacked to do that. But he's absolutely right, because what did God do on day 4? He made the luminaries, the sun and the moon and stars, but that implies, I think, everything else out there, things you can't see with the naked eye, including galaxies. And he said it was good on the end of day 4. And at the end of day 6, he said it's very good. And what's that goodness referred to? It refers to things functioning the way they're supposed to, fulfilling the purposes they're supposed to. And I take it from that the galaxies were formed mature. God didn't make baby galaxies. He made fully mature galaxies to start with. And that's our creation model. And Jason Lyle predicted that, and that's exactly what we've seen so far. That's impressive when you think about it. He was right. I knew he was right. I just wish I had thought of it. There's no rivalry between us, but I have my good days, and he has his good days, All right, what about the composition of distant galaxies? Well, there's a little interesting fact here. According to the Big Bang, the universe starts with hydrogen and helium and a little bit of lithium. Those are the first 3 elements in the periodic chart. And by the way, the lithium there, a lot of it gets destroyed when stars start to form. It kind of consumes those. So lithium is difficult to tag. There's not much of it anyway. That's why we're having trouble getting enough lithium to keep all those new cars running on that stuff. It's amazing what they're doing there. All heavier elements, carbon, nitrogen, oxygen, calcium, iron, silicon, just a few examples. They were forged later in stars. We call this chemical evolution. By the way, chemistry to astronomers is real simple. We've got three things: hydrogen, helium, and metals. Oxygen is a metal, carbon's a metal, nitrogen is a metal, sulfur's a metal. They say, well, they're not metals. Okay, they aren't. But if you get past the first two elements of the periodic chart, more than 80% of the other 90 naturally occurring elements are metals. So we collectively call them metals, even though they don't include. So they have hydrogen, helium, and everything else we call metals. There weren't any everything else to start with. So the first stars form, and they take some of that hydrogen and fuse it and form it into helium. If it's a massive star, it'll burn all the hydrogen it has, its fuel in the core. It'll shrink down, get hotter, it'll start to transform some of that helium into carbon that never existed before. If it's really massive, we'll run out of that helium fuel, and it'll start fusing alpha protons, nuclei, alpha particles, onto that carbon. They'll produce oxygen, and I'll work your way up by twos to get your way up to iron. When it gets to iron, you're pretty well done. But then, if it's a really massive star, it will explode. The core will implode, boom, the rebound will blast the star apart, and it will take some of that material, the sulfur and iron and other things. By the way, when it explodes, it will make the transferric elements, the heavier elements out there. Blows it out into space, what's called the interstellar medium. It mixes with a few of the stars, the gas already out there, and then somehow a miracle happens and more stars form, and now they have a little bit of the heavier elements. And these stars begin to do the cycle all over again, turning hydrogen to helium, and then helium into carbon, and carbon into oxygen and other things, and eventually it explodes and spews some of the products of that nucleosynthesis out into space, which it then mixes. It's a continuing process. Each time you get a new generation of stars, the amount of the heavier elements increases like that. And after 12, 13, well, actually about 9 billion years when the solar system formed, we get this. And it's still mostly hydrogen helium, but the Earth is blessed with a different suite of these. We got rid of the hydrogen helium, and we're left with the more rocky stuff. And as Lawrence Krauss likes to say, we're stardust. All of these elements we find here, these heavier elements, formed in stars. You know who Lawrence Krauss is? He was at Arizona State. He still may be there. And so he likes to talk about the fact that the iron in our blood and the calcium in our bones were forged in stars a long time ago, billions and billions of years ago, before the solar system formed 4.5 billion years ago. The iron in your blood may have been forged 10 billion years ago. And pardon me for quoting him here. I'm going to quote him. It's really not good, as Christians should not speak this way, but I'm quoting him. He's speaking to a lecture at a university, probably Arizona State, I don't know. It's on YouTube. And he talks about how poetic it is that, you know, some of the iron in this hand and some of the calcium in this hand formed in different stars billions years before there was a solar system. And he says, forget Jesus. The stars died for you. Yeah, that's blasphemous. Well, how long do you think it takes to form a lot of carbon and nitrogen and sulfur, oxygen, and all those things? It's going to take a while. But guess what they're finding? They're starting to do spectroscopy. When they do, they find that heavier elements are found all the way back. Those early galaxies they find, they have the heavier elements already there. Not only the galaxies forming sooner than they should have, the stars forming, but the stars are producing the heavier elements at a very fast rate, faster than they should. You're getting all these elements showing up before they should. Also, they're forming dust, and dust you can't make out of hydrogen and helium. Dust part of the little microscopic bits. They're formed out of silicon and oxygen and iron and things like. What do you get when you put silicon and oxygen together, Nate?
Yes, sand.
You get silicates, right? A lot of the rocks on the Earth. That's where it came from. Stardust, once again. But you know what? You not only need a bunch of generations of stars to forge those elements, but you have to make the dust particles. And you can only do that in another generation of stars. So they keep piling generation on generation on generation. And all those generations are compacted together. And so again, you got all these elements, heavy elements, you got all this dust in the early universe. They're even getting molecules are detected, which takes a while to put together as well. And the whole point is there's very little evidence of this chemical evolution, gradual buildup over time. It's like all these elements were full blown in the early universe. And again, that's consistent with what we expect because it is very good that God proclaimed at the end of all of this. Well, another thing that leapt out about a year ago, this is interesting, actually earlier this year, I believe, they used the JWST to look at some distant galaxies. They studied 263 galaxies. And they noticed that they could measure or they could determine the spin direction. You know, some would be spinning this way, clockwise, counterclockwise as you're looking at it. Others would be spinning the other direction. You expect in the universe, with a sample size that large, you expect somewhere around 130 of them to go clockwise and about 130 of them to go counterclockwise. That makes sense? If they're truly random. If you flip a coin 263 times, you're probably going to get something close to 130 on either side. But what they found is that most of those galaxies go one way. And the way they're going is opposite the way the Milky Way turns, making the Milky Way kind of odd. Now that's weird. That is weird when you should have a random distribution, but you don't. It's skewed in one direction. Nobody knows what that means. But it shows that the universe is not isotropic. And that's one of the fundamental assumptions of the Big Bang model. The universe is homogeneous, that is having the same properties everywhere, and isotropic, having the same properties everywhere you look. Every direction you look, and that's obviously not the case. By the way, there's other evidence that the universe is not isotropic. And if the Big Bang model is based upon isotropy, then, and isotropy is not true, the Big Bang model cannot be true. Very quickly, I'll talk about the atmospheres of exoplanets. And I pointed out the fact that what's really going on here is they want to look for Earth-like planets, because if you can find an Earth-like planet, that means you got liquid water and all this sort of stuff. There's probably life on these. And by the way, if you would have gone back say 30 years ago, and you would have asked scientists and astronomers particularly, when we find over 5,000 exoplanets, how many would be Earth-like? I think most of those scientists would have said, oh, hundreds of them. How many of those 5,000 plus exoplanets are Earth-like? Zero. Keep looking, folks. Every day you do that, you're backing us up, because our model, we believe that the Earth is unique. God specially made it to be inhabited. And that's our prediction as well, and it's bearing out. But let's get to the planets do have atmospheres. Several of the planets in the solar system do. So how can we find out what the atmospheres of some of these exoplanets are? Well, the way we're going to do this is look at transits of exoplanets, and this is the most common way that exoplanets are found. We have there a yellow ball that represents a star. You got a little red dot that represents a planet. It's going to be a lot smaller than a star is. And so if you're looking at its edge on, its orbit, now if it's orbiting like this, nothing's going to happen. But if it's orbiting like this, once every orbit, that planet's going to pass in front of the star. You can see the little red dot passing in front of the star there. And what that's going to do is it's going to dim a little bit of that star. All right? And so if we're some distance away, hundreds of light years away, and we're looking at this star, what should happen is periodically the light of the stars ought to dim a little bit. You got a light curve there at the bottom. Notice the brightness goes constant. It's going across the plot like this, and then it dips down like this, and then it recovers like that. You see what I'm talking about? And by studying the shapes and depths of that light curve, you can figure out things like how big these things are. Now, when they first started discovering exoplanets back in the 90s, I was skeptical. The way they were doing it was some sort of Doppler motion, and the Doppler motion was really feeble. They were using computer technology to tweak out the signal, but there were a lot of things going on in stars, like pulsational motions that could mimic that. So I was suspicious. But then around 2000 or so, they found one transiting planet like this. Well, this is very similar to the work I do with eclipsing binary stars. I've been doing eclipsing binary stars for over 45 years. And what we do is we look at two stars that are real close together and they're orbiting each other. You can't see the individual light because they're too close together and too far away. It looks like one star. But periodically, one star passes in front of the other. When it does, it causes a dimming of the light. And then a half cycle later, the other one returns the favor. So you get this dip, and then it repeats, dip and dip like that. And by studying the depths and the shapes of those light curves, we can figure out things like the sizes of the stars, separation stars, and a bunch of other things. And I've been doing this for almost a half century. It works. So when I saw this, I thought, okay, I'm convinced there are exoplanets. And this is most of the way we find these things now. We have these orbiting telescopes that survey thousands and thousands of stars very quick. In fact, one of them, Kepler, was doing like, I don't know, a million stars or something every 20 minutes. Every 20 minutes. And being above the Earth's atmosphere, you don't get the blurring, which can mimic it. Now, let me put this real to you. I told you before, I believe the sun is more than 100 times the diameter of the Earth, so that dot's going to be pretty small. But if you're an alien planet looking back at the Earth as it transited in front every year, every 365 days, the Earth would dim the sun by about 1 part in 10,000. That's about 1/100 of 1%. And it would do it for about 6 hours. Now, that's not much of a dimming, but our capability is far better than that now. That's the reason why we can do it. You want to see some real data? That's real data. That's fake data on the top. This is real data. Pretty good. You get this light curve. The light's pretty constant, fluctuating a little bit, 1 part in 10 million or something, and then down it goes and back again. By studying the depths and shapes, we can figure out something about the star itself, but particularly with the planet, we know how large that planet is. This is how we find most of them this way. All right. Not only does the planet block out light, but there's an atmosphere. If there's an atmosphere around it, it's going to have this ring around it of gas, a cool gas. And as that light, I'll put it towards you, here's the star, here's the planet in front of it, that little ring of gas around it. As that light, the sun, that star passes through that, it's going to be absorbed a little bit by that atmosphere. And the absorption occurs at certain wavelengths. This happens all the time in astronomy. That's how we measure what stars are made of, because they have absorption lines in their atmospheres. They have what's like an atmosphere around them. And it turns out, when you're looking at molecules particularly, they just happen to be in the infrared, which is what the JWST is very good at doing. So what they're going to do is they're going to look for Earth-like planets. They're going to have to look for what 2 gases? What's the most common gas in the Earth's atmosphere? Nitrogen, diatomic nitrogen, N2, right? 78% of what we breathe is inert nitrogen. What's the other 21%? Oxygen 2. The other 1% is everything else. So we're awash in all this nitrogen and oxygen. So if you got to have an Earth-like planet, it better have a nitrogen-based atmosphere with some oxygen in it. Well, it turns out N2 and O2 are detectable in the infrared. So the JWST is perfectly suited to do this. And they're starting to do this now. What they have to do is figure out from our previous observations, when a particularly promising planet is going to transit, you turn the JWST, if it's available and it's not too close to the sun, then you can observe it and look for those things. And they're starting to do this. It was just in a story last week or two about one that's Kepler 19b, I believe. It really was not a habitable zone planet. They were looking for an atmosphere, and they didn't find one. There were no absorption features they could see. That was a bit of a disappointment. This phase of the study of the JWST is just beginning, and so consequently the results are not really in yet. It's going to take a while for this to happen. That's the second key project. Stay tuned, so we're going to have more and more of this. So in conclusion, what do we got? Well, the predictions of the evolutionary model of the formation of stars and galaxies in the early universe has been falsified. Now, in the same world, we'd say it's been disproved. You got to go all the way back to the starting place. The stars and galaxies formed too fast. The heavier elements and dust appeared far too soon. So it looks like the standard theory of how the early universe evolved after the Big Bang is completely wrong. So if you're an evolutionary astronomer, what are you going to do? Well, you're going to take the data, and you're going to go back and you're going to change the model. You're going to modify the theory so it matches the data. All right? And I guess you can do that, but what you can't do is turn around and claim that the data now prove the theory. Now, back in 1989, they launched a satellite called the COBE, C-O-B-E. Remember that one? Before your time, a lot of people weren't born yet. COBE was a big deal because they had a 2-year mission from 89 to 91, and they were supposed to map the cosmic microwave background, the CMB for short, very precisely. The CMB was discovered in 1964. It was the first evidence for the Big Bang, and it actually caused the Big Bang to become widely believed. Before that, it was not believed. It was rejected. After that, by 1970, almost every astronomer and most scientists believed the Big Bang, and that's been the only game in town for more than a half century. Now, the model predicted that in the early universe, you had to have some structure there. You had to have seeds of material where the Big Bang gas was a little denser in some place, a little more rarefied. That denser area had a little more gravity and began to pull material towards it, and that would develop into stars and galaxies, robbing material around it until that structure gave rise to galaxies and clusters of galaxies we see today. Without that happening, we wouldn't be here because the universe would be too smooth. Would never form structures like that. And so they predicted back in the 70s and early 80s how much clumping of material they should have, and that clumping in the early universe would show up as slight temperature variations in the cosmic microwave background. And they predicted that those little fluctuations of warmer and cooler air, more dense and less dense, would be temperature variation about 1 part in 10,000. The CMB is a temperature a little less than 3 Kelvin, so we're talking like variations of 0.0003 Kelvin. That's pretty impressive. But the detector aboard the COBE satellite was able to do that. So after 2 years of data, what do they find in the CMB? Perfectly smooth. So what happened to the prediction of the Big Bang model? It was disproved. Now they did tweak the results, and they were able to, by very sophisticated techniques, discover that there were fluctuations on the order of 1 part in 100,000, not 10,000. And later on, that was confirmed by other experiments. They had 2 more satellites that mapped it once again, and they found that fluctuation on the order of 1 part in 100,000. How far off were they? A factor of 10. Let's suppose that you want to guess my weight. And one of you guesses that I weigh 19 pounds, and the other one guesses that I weigh a ton. Either one of you are off by a factor of 10. Is that pretty good or pretty bad? That's beyond pretty bad. It's horrible. That's how far off they were. They're off by a factor of 10. So what was their fix? They took the data, they redid the theory. And I have heard people claim, Hugh Ross was one of them. I heard him in a presentation say that the observations beautifully matched the predictions of the theory. I'm saying, don't lie to me. Don't call me a that. It did not match the prediction. What you did is, and then you redid the model, and then you're trying to claim it proves the model. It doesn't. It just means that you match the model pretty well to the data, but it doesn't prove the model at all. Let's suppose at the end of the presentation tonight, I'm going to give you a test. And this quiz is going to test 2 things: how well I've instructed you tonight, and how well you learned, and how well you paid attention. Anybody afraid to take this test? Okay, I'll make it afraid. It's going to be 1 question. So it's basically pass-fail. Now are you afraid? Anybody afraid of this test? You're going to flunk tonight? Yeah, you're afraid, aren't you? All right, I'm a nice guy. I'm going to help you out. I'm going to tell you the answer to the question. All right, you ready for this? You want to write this down? You got to write this down, because this test is going to pass-fail you. You ready? You listening? The answer to the question is 42. Yeah, some people get that. 42 is the answer. Did you hear me? 42. Okay, how many of you are going to ace this test? Nobody raise your hand. What's the matter? You're dumber than a sack of rocks? You don't believe me? What's going on here? What's the answer? 42. Everybody's going to ace this test, aren't they? Everyone's going to ace this test. Now, does that really prove anything about what you learned tonight, or about how I taught you? Absolutely not. You cheated. I cheated. That's exactly what they did with the COBE data, and that's exactly what they're doing with the information from the JWST. It disproved their model in many ways, 3 different ways at least. So what they're doing now is they're going back and they're redoing their models. How can we get this structure to form much earlier? How can we get all these metals to form so much earlier? And how can we have it occurring earlier than we ever thought? And when they come up with this new theory, you know what some people are going to say? They're going to say that the data from the JWST perfectly matched the prediction. We'll do it again, folks. And that's just not the way science is supposed to be done. You can constrain a model that way, but you don't tell me you proved it, because that's circular reasoning. That doesn't prove anything at all. What about the exoplanet atmospheres? It's too early to tell. But I'm going to go out. I'm going to pull a Jason Weil here tonight. I'm going to make a prediction. They're not going to find any Earth-like atmospheres, folks. I'm pretty sure that's the case. Make book on that. No diatomic nitrogen, oxygen atmospheres out there. And I would say, as Jason has said, the stars and galaxies and heavy elements and dust at great distances, not look back time, not early universe, but almost real time, they are consistent with what we expect of the creationary model. So my conclusion is the evolutionary models are in trouble because of the JWST, and the JWST results so far have given evidence for the creationary model. Thank you very much. I'll be happy to answer questions.
questions?
I'm not smart enough to ask it. Very nice, though.
Thank you.
Very,
It doesn't have to be on this presentation. It can be other areas of astronomy if you want. Or any other areas that you think I can take a stab at.
You pass up the test while it's still fresh.
Pardon?
You pass up the test while it's still fresh.
Take out a half sheet of paper. How many people have heard that from college? You know? And how many got my reference to 42? Yeah. I have read all 5 books in the Hitchhiker's trilogy. Anybody else read all 5 books in the trilogy? No? Good stuff. Any questions? Maybe we should ask them questions.
So Danny, you talked a little bit about some of the distances that, the secular astronomy talks about as far as these galaxies. I know one of the itchy questions people oftentimes have is, how do we in creation explain those distances within a younger creation model, perhaps?
Okay, I got a whole presentation on that. You want me to answer in 3 minutes, probably. I'll give you the short version. I'll give you the elevator pitch on an elevator that stops at every floor. All right. So the light travel time problem, the way it's usually formulated is we can see things out to thousands of light years, and that would cover all the stars we see at the naked eye, at least. But again, I saw Andromeda the other night, a couple of nights in a row, with my eyes, naked eyes, and it's 2 million light years away. So how can we see anything that far away? It seems like if the universe is, say, 6,000 years old, and it's a little older than that, but not much, 6,000 for the sake of argument, how can we see anything beyond 6,000 light years? And I would submit to you that question is improperly formulated. Because you see, Adam had a light travel time problem. God made the stars on day 4, made man on day 6. That's a 2 days difference. So Adam should have not seen anything farther away than 2 light days. Now it's okay with the sun, it's only 8 minutes away. The most distant planet we can see with naked eye, Saturn's about an hour and a half, so that's okay. But the nearest star is over 4 light years away. Sirius is about 8.5 light years away, and Vega is about 26 light years away. So what did the first night that Adam and Eve looked up in the sky when night fell, did they see any stars? Did they have to wait for years and then one star appears and eventually another star appears? No, I would submit to you that Adam and Eve saw pretty much what we see today. The Bible doesn't say explicitly it says that, but I think I can prove it very quickly. You see, I talked about the good of day 4 and the very good at the end of the creation week. And what does that goodness mean? Well, that goodness refers to the completeness of creation, that everything that God made is doing exactly what it was made to do. It's fulfilling its functions and purposes. For instance, God rapidly made the plants on day 3. Everybody for the longest time thought there's just poof, there's a palm tree, poof, there's an oak tree, out of nothing, just bam, appeared. That's not what the text says. The text says that God caused the plants to grow up out of the ground like this. You ever seen Eric Cohen's movie Genesis, Paradise Lost? And he goes through the days of creation. I love day 3 because he has these plants coming out. It's creaking and crackling, and branches are forming, and fruit and leaves. It's exactly how I imagined it being. God used a process to do that. Why did he do that? He didn't make seedlings that stayed seedlings. He didn't poof make them instantly. What he did is he grew them up all in a day, less than a day. Really, why? Because, was it verse 29? I never can remember if it's 29 or 30. It says that everybody ate plants to start with. If all the thing everyone would have grown gradually, like they normally do today, everybody would have starved to death. They fulfilled that purpose that was given to us at the end of the chapter. Likewise, the stars and heavenly bodies are given purposes in the day 4 account. But the thing is, they could not fulfill those purposes if they were not visible. So what I think happened on day 4, God makes the heavenly bodies, the nearby planets and the sun and the moon, but he also made the most distant galaxies and quasars. And he rapidly brought that light to the earth, miraculously, just so that made the plants grow up. That's the reason why I say I'm looking at Andromeda pretty much close to real time, not 2 million years ago, but 6,000 years ago. The light was rapidly brought here. You know, I share this with lay audiences, and most people like it. In fact, I've had lay people tell me, I thought that for years. And I said, well, thank you. I didn't. That was too stupid. I couldn't get it like you could because I knew too much. That was the problem. Education can be hindered sometimes. And but when I share it with the physicist, through a creation scientist, they don't like it. You know why they don't like it? They're looking for a physical mechanism. we're talking about the creation week. Can you think of anything else in the creation week that was physical or natural? Let's see, there were no plants and then there were. There was no man and then there was. There were no animals and there was. There was no matter that there was. There was no light that there was. I mean, you go down the list, everything in the creation week is miraculous. So why do you hold out one thing in the creation week and you have to explain it naturally? That's inconsistent. We have a name for that. It's called uniformitarianism. We don't let the evolutionists get away with it. How do we let our creation brethren get away with it? So I have no qualms today. I was searching for years for a natural physical explanation, and it was in plain sight. It's a miracle, and I shouldn't apologize for that. That helped. How long did it take? About time?
4.5 minutes.
It was a very slow elevator. Is what it was. Yeah.
So, you briefly mentioned as the because it didn't quite fit their predictions on it, but the cosmic microwave background is often touted as one of the evidences that convince so many people that the Big Bang is true. How do we explain that background radiation? How does that fit a creation model?
For many years, I would give a presentation, starting in the early 90s, give a presentation on the Big Bang and explain what scientific problems were and what the biblical problems were. It's usually talking to a Christian audience. And, some Christians believe in the Big Bang model. In the beginning, with the Big Bang, God created heaven and earth. That's sort of the way they read Genesis. And I would admit in the talk that the CMB was a prediction made 17 years before it was discovered, 16 years before it was discovered. It was not looked for because there was no technology yet to do it. By the 60s, there was the technology. And the only other model out there was the steady state model, which was the preferred model for a few decades. But it did not predict that there could not be any cosmic microwave background out there. But the Big Bang predicted it. And when they found it, then it eliminated the steady state, and it was evidence then for the Big Bang. Now, does it prove the Big Bang? Well, what do you mean by proof? In science, we don't prove things the way people understand proof. If you do a mathematical or logical proof, you know without any doubt that what you proved is indeed true. But when we say proof in science, what we really mean is we found evidence that's consistent with our hypothesis. It's an if P, then Q sort of situation. We found if you know that P is true, then you know that Q is true. But we're not doing that. We're finding out that Q is true. Does it follow then that P must be true? And the answer is no, because it's a logical fallacy called affirming the consequent. So you see, there could be some other theory out there that could explain it equally as well. And that gets down to what Thomas Kuhn talked about in science of disproving things. Not Thomas Kuhn, Sir Karl Popper. He said in science we look at ways to falsify our theories, and if we try again and again and again to prove that a theory is not true, then we get more and more confidence that it is true. We're giving evidence all the time that it's not absolute ironclad proof. So therefore, the CMB doesn't prove the Big Bang. What it does, in a sense that most people understand, what it is evidence consistent with it. I'm not afraid to admit that because it was predicted before it was found, and we're done. And I remember I gave a talk early on, and this Christian man who believed the Big Bang, and he came up afterwards. He said, "Well, if the CMB is not from the Big Bang, what's it from?" And my answer was, "I don't know," which is a good answer if you don't know. Don't try to snow people by giving an answer you don't really believe or know. And I got that question a few other times as well. And I was always honest to say, I don't know. I wish I knew. Well, when I went to work for Answers in Genesis 12.5 years ago, I kept a list at the university. I had a list of projects that someone ought to do. I could do them, except I was busy and I didn't have time to give my full attention. I have an afternoon free, and I'd spend it on it. And then it would be 2-3 weeks if I'd come back to it. When I did, I'd start all over again. Couldn't remember where I was. If I worked on it day after day, I'd be fine. Well, when I came Answers in Genesis, I brought my list, and now I wasn't wasting my time teaching classes and stuff. I was a full-time researcher, so I could spend time on this. And I spent several weeks on this. I talked to Hebraeus, I was talking to theologians, looking at all sorts of people to try to figure out what my model was going to be. I was going to say, what is the biblical cosmology? I'd wrestled with that for years. By the way, when I finally got it, I shared it with John Albert on a trip. And John said, I always thought that. Again, I'm held back by knowing too much, And I had other ladies who said, "Yeah, I always thought that too." Why didn't you tell me? Actually, there was somebody back in the late 70s who tried to tell me, and I didn't listen to him, so I was warned. But here's the rub. I looked at it, And I wanted to find out what this thing God made on day 2. The King James, it's firmament, which is a horrible translation. The Hebrew word is rachia, and it means expanse. And so modern versions say expanse. So God made this expanse. I'll roughly quote to you verses 6 through 8. And God said, let there be an expanse to divide the waters from the waters. And it was so. So God made the expanse to divide the waters above the expanse from the waters below the expanse. And God called the expanse heaven, and the evening and morning were the second day. That's it, folks, not much. Doesn't tell me too much to work on. But then you skip together verse 14 through 19, which is day 4, and he says, let there be lights in the heaven, an expanse of heaven to give light on the earth. And God made the lights in the expanse of heaven with the different purposes. And God placed the lights in the expanse of heaven. You see a trend there? 3 times it says in the creation account, day 4, it says where he put the luminaries is in the expanse of heaven, expanse of heaven, expanse of. When you repeat something 3 times, what does that mean? Hello, pay attention. This is important. And it hit me. I thought, wow, why is he doing that? I think he's trying to tell us. He just made this thing. It was an expanse, and he called it heaven. So when a few verses later he says expanse of heaven, I'm inclined to think it's talking about what he made on day 2. That's quite an insight to me. You see, I've been led down the wrong path because Henry Morris and John Wickham, you know those names. I hope you know those names. They loved the canopy model, and they thought that the Earth's atmosphere was the expanse, and God made space, as it were, on day 1. But it doesn't fit the biblical text very well at all. And by the way, most creation ministries dropped the canopy model years ago, but nobody bothered to go back and re-exegete days 2 and 4. If it's not the atmosphere, then what is it? So I did that. And so I look at it with a 21st century viewpoint. Where do we say that the heavenly bodies are today? They're where? They're in. Where's the Andromeda Galaxy? Where's the sun? Where are they? They're in space. That's a modern term, folks. I'm a 21st. Well, actually, I'm more like, well, I'm a guy living in the 21st century who's not convinced the 20th century was a good idea. But anyway, I'm somewhere in modern times, and so I'm going to use the terminology that I know. And that puts them in space. Now, as it turns out, birds are said to fly across the face of the expanse of heaven. That's in verse 20 of Genesis 1. That face tells me it's the near side of it. So basically, it's everything above us. And today we would distinguish between the atmosphere and space. Now, you don't get that in the Old Testament. You get something like it into that. But this is the modern imposition. And where's the difference? Where does atmosphere end and space begin? It doesn't. It's kind of a continuous thing. We just arbitrarily decided the separation there. So I would say that on day 4, day 2, God made everything outside of the earth, which didn't exist before that. Think about that. Space outside the earth didn't exist on the first day. It was the second day it did. And that made me feel pretty good. So I finally get this all together after weeks. And so I come in and I'm writing this up for a paper for the Answers Research Journal, our online research journal we have. And I'm working on this for probably a week and a half, typing it up. And I wish I would have written the date down, because I came in one morning at the office and I started typing, and suddenly it hit me. What did the expanse do? It divided waters below from waters above. So if it's space that's there, then where are those waters above? It suggests that there's water at the edge of space. And that rocked my world. Because here's what I think is going on. Since this was expanded off the Earth, you go out so far and it stops. Space stops. Almost no other astronomer thinks that. And not only that, there's water at the edge of that space. Nobody else thinks that. Since it's roughly spherical, I'm just assuming it is. In physics all the time, we start with everything's spherical. There's nice symmetry. There's even been a joke about, physicists approximate cows as being spheres. Only in physics do you have spherical cows. But if it's something spherical off the Earth, that suggests the Earth is somewhere near the center. And most modern astronomers would say, even if the universe had a center, which it probably doesn't, what's the probability the Earth would be near the center? Well, I'd say 1, because that's the way God did it. But they're arguing without a God. So if you made this big universe with a center, the probability if you randomly drop the Earth some way is vanishingly small, be at the center. So I'm really swimming against the current here. Then it occurred to me, I'd already was discussing, this is what the real big idea that hit me. I suddenly realized that water at the edge of the universe has a temperature. That's the third law of thermodynamics. I've never heard that one. There is a third law of thermodynamics. And anything, I talked about this earlier tonight, anything that has temperature has to radiate. Many of those radiation will be in the infrared part of the spectrum. But since it's coming a great distance, it's coming a huge distance away from the edge of the universe, it's going to be subject to that redshift that we observe. And so it's going to be shifted even farther out of the infrared down to probably the microwave part of the spectrum. And just it fell out and tumbled right out. I wasn't looking for what the CMB is, but today I think the CMB is radiation from that water at the edge of the universe. You just got two 2-hour talks in just a few days. It's amazing.
We're getting our money's worth.
One of them was the elevator going to the top, and the other next was the elevator coming back down. 2 elevator pitches in tonight. Yes.
What's your take on like the theories of dark matter and dark energies? Do you have any like explanations or theories about that?
I've written quite a bit on that, spoken quite a bit. I'm very bullish on dark matter. For some reason, I don't know if you've noticed this, but creationists, many of them do not like dark matter. And I think the reason why they do is because they came to the party kind of late. They started hearing about dark matter about 25 years ago. And all they heard about dark matter was this happened in the early Big Bang. This big dark matter did this, and dark matter did that. And they said, whoa, dark matter is a rescuing device. They just made it up because they had a problem in the Big Bang theory. And so they had to come up with something to salvage it. And so they made dark matter up to salvage that. That's not what happened at all. It makes it sound like astronomers and cosmologists really quickly ran to this and embraced it. Nothing could be further from the truth. Anybody know when the first evidence for dark matter was published? 1935. Yeah, long before the Big Bang was accepted. It had been thought of, the early version of it, but had not been accepted at all for another 40 years. The next bit of evidence came in 1939. One of them was Fritz Zwicky, who was looking at clusters of galaxies, and he was trying to get the masses of these things, and he found out he could find the mass by what we call lighted mass, by measuring the light of the galaxies in this cluster of galaxies, knowing how much mass was in each galaxy. He could multiply together, and that gives you how much lighted mass there is. Then he had what's called the dynamic mass. He could measure the orbital motion these galaxies had individually, and that will tell you how much dynamic mass, how much mass in Newton's law of gravity will tell you is required to produce that orbital motion. And he found in the Coma Galaxy cluster, he found that the dynamic mass exceeded the lighted mass by about a factor of 10. Wow, big mismatch. So he goes to another cluster and he finds the same result. Everywhere he goes, the same result. Meanwhile, in 1939, a guy named Babcock is looking at the Andromeda Galaxy, it's nearly edge on. He measures the speed of a few things as they orbit around. And inside the nucleus of the Andromeda Galaxy, things move about what you expect. You get this lighted mass in there, and you can predict how much it would be. And as you get out beyond that, the speed should decrease because the light is decreasing. There's less mass out there, and the speed should drop down. So the speeds in the middle, going from the origin on to rise very quickly, reach a peak, and then fall back down. It's called Keplerian because it follows Kepler's laws of motion. Except they don't. They're way up here. They should be going down. They don't. Things on the outside of galaxies are moving far too fast. The only explanation for Fritz Zwicky's result is that there's more matter there than we're seeing. It's dark, doesn't give off any radiation. And the same thing was true of Babcock's result. 1930s, nobody paid attention. Nobody wanted to look at it. Finally, a woman named Vera Rubin, I met her once. She's, and starting around 1970 or so, she starts going back. The technology had improved. When Babcock used the 100-inch telescope, he was pushing it to the limits of what could be done. But when Vera Rubin comes along, we have bigger telescopes and we have more advanced technology that can record much fainter things. And she started repeating what Babcock did on the Andromeda Galaxy and really nailed it down. There was way too much orbital motion that could be accounted by the lighted mass. She goes to another galaxy and finds the same result. Another galaxy. She has scans of papers over 10 years. And by 1980, astronomers are saying, you know what? She's right. There's far too much mass out there, about 10 times more mass than we're seeing. And they called it a missing mass for a while. They started calling it dark matter, which goes back to Fritz Zwicky. He wrote in German, and he called it Dunkelmatter, which is literally translates as dark matter. So in the 1980s, finally astronomers woke up and smelled the coffee and realized that dark matter is real. And about a decade later, in the mid-90s, cosmologists began to realize something and said, wait a minute, gravity is a dominant force in the universe according to our theories. And we've been leaving out 90% of the mass in the universe. How good could our models be if we're going to leave out 90% of the mass? Can't be good at all. So they started in the late 90s, mid-90s, started talking about dark matter in the universe. And that's when some creation astronomers, creation scientists, mostly physicists, started paying attention. They didn't know about the 60-year history before that. I did. In fact, other astronomers know as well. Turns out astronomers who are creationists are almost completely unified. Dark matter is real. We better deal with it. Yet the physicists have a hard time with it. I don't know what their problem is. I've explained it to them over and over and over and over. Well, they're like me. They know too much, or they think they know too much. I'm sharing the information they need to know, but they don't pay attention. I don't know. I don't get it. Dark matter, on the other hand, I mean, dark energy, on the other hand, is something different. I don't like that term because it's suggesting something, they're very different. But the Hubble relation, I'll talk about the Hubble relation. I showed that in an earlier plot, what it looks like, the Hubble relation. I'll come back to it. Yeah, you go out to a great distance. Nearby, you have distances close by, and you go farther and farther and farther out. This is assuming that the expansion of the universe has been constant. But they realized that if the universe was should be slowing down because there's gravity here. It's slowing down. If you show a rocket up into the air, and you stop, the engine burns out. It's going to start slowing down because it's working against gravity as it tries to go up. Same thing in the universe. It's expanding, but the gravity in the universe starts slowing it down. So they expected when they went really, really, really far out, the curve would depart from linearity. It'd start to turn up or down one of the ways. And they predicted on the basis of the universe slowing down its expansion, it would deflect one way. So in the 1990s, the technology got to the point they could use what are called type 1a supernovae, which are very bright, and they're also very uniform in their brightness. So you can use them to find distances to galaxies that are billions of light years away very accurately. And they understood, there were two teams working on it, independently, didn't know about each other, and they understood that it should start from linearity one direction out there, due to deceleration due to gravity of the universe. They found out was deviating the other direction. Both teams were tearing their hair out trying to find out what the problem was, and then they found out about each other. They got together and compared notes. They were working a little differently, but the same thing, and they realized they weren't both making the same mistake. They were both doing it right. Big surprise, they were expecting the universe expansion to slow down. It wasn't. It was actually speeding up. Now, this, when interpreted in terms of the Big Bang, is unacceptable. It's unavoidable. The universe is getting faster and faster in expansion. But what if you don't have a Big Bang cosmology? Well, then it might mean something else. So when it comes to creationists, how do we explain it? We need a cosmology, but we don't have one. So I can't tell you what it is in terms of the cosmology. I can tell you what it is in the Big Bang, but in terms of, we reject that. So what does it mean to a creationist? I don't know. Ask me again in 10 years, maybe we'll know that. I think it'll be somebody else answering the question other than me, though. Does that help? I just took 6, 7, 8 minutes to say I don't know. That's what we had a whole seminar class for a whole semester in grad school to learn how to say I don't know in 10 minutes. Anybody else? Every one of those questions require one answer. I could have said I don't know. That would have been fast. Any other questions? Hey, you want to wrap us up?
All right.